Okay, so we're going to actually start doing some statics now, okay, where we're going to look at some equilibrium. But before we do that, we have to talk about a couple of specific forces that we might see in some of our statics problems, okay. The first one is talking about springs, okay. Now, a spring is basically an elastic member, okay, whose length changes proportionally to a force using this equation, F equals Ks, okay. F being the force, K being the spring constant or stiffness. So the bigger K is, the more force it's going to take in order to get that thing to change its length. Okay. S is what we call the deform distance, which is L minus L naught, which is the current length, L, minus the unstretched length or the undeformed length, L naught. So S is the difference between those two. Okay, and if this spring is being elongated, that force, it's requiring a pulling force to get that spring to do that. If the spring is being shortened, that's a pushing force. So you want to draw your force accordingly, depending on if it's being pushed or pulled on that spring. Okay, so again, the spring is nothing more than the stiffness times the change in length or the stretch, okay, which is the current length minus the undeformed length. Okay, the other thing we want to talk about is cables, and we've already dealt a lot with cables. Okay, just a few assumptions that we always make about cables. The first one is that the weight is negligible, so we don't have to worry about gravity acting. Generally, they're much smaller than the loads we're dealing with. Okay, the other thing we assume is cables don't stretch. Okay, obviously they stretch a little bit in real life, but not an appreciable amount that we need to worry about. Not like a spring would stretch. Okay, so we assume cables do not stretch. Cables can only handle tension. If you don't believe me, try to compress some string and it'll just fall down, limp. Okay, so I always know that if it's a cable, it's in tension, so it's basically pulling. Okay, we've talked about this many times before. The force is obviously in the direction of the cable, so we can know the direction of that force. Okay, and the other thing is that the tension, the force, is constant throughout the cable. So if I have a pulley system right here, the tension over here equals the tension over here, assuming this thing's in static equilibrium. Okay, so no matter where I look at the cable, it's going to have the same force going throughout the cable. Okay, so those are some things to think and remember about cable. Again, we've dealt a lot with these, but those are the assumptions that we're making anytime you see a cable. All right, so how do we actually deal with this 2D particle equilibrium? That would be a body that has forces acting on it, not moving. So the first step in any one of these problems is to draw a free body diagram. Now, a free body diagram is basically the body, or in our case, the particle. Okay, we draw it free from our surroundings, and we show all of the forces that are acting on that body. And we make sure to label everything, even if we don't know it. Okay, so if we know the force, we say what it is. If we don't know what the force is, we just call it unknown. We may know the direction, put that in there. If I don't know the direction, give it a label. Okay, and if you have any unknown force, you can just make an assumption that it's in one direction or another. Okay, and you'll see what happens if you make the wrong assumption. It's not a big deal. Okay, so an example that I have here is just a lamp being held from with this cable, this spring. Okay, the particle I'm looking at is actually A, and that's what I draw my free body diagram. So there's A. I don't have anything else. I'm just that little ring there. I have the weight of the lamp known at 78.5 newtons, so I draw that down. I have this spring force acting in the X direction. I'm assuming the spring is elongated, therefore the spring's pulling on it, maybe pushing on it, and I'll just make the assumption that it's pulling on it. And then I have this tension in cable AC. I know that's in tension, so I know it's pulling on point A, because cables have to be in tension. So that's a free body diagram of the drawing we have above there. Once I have my free body diagram, I basically apply my static equilibrium equation, which states that the sum of the forces equals 0, because Newton's second law says the sum of the forces equals mass times acceleration. Well, the acceleration is 0. Sum of the forces equals 0. That's my equilibrium equation. So we just sum up all the forces in all the directions, set them equal to 0. Now, remember, we may have made some assumptions about unknown forces, about which direction their arrow is going. Okay, if I assume it's going, say, to the left, and I get a negative result for that force, it's actually going to the right. Okay, so any negative result that you get just means that your free body diagram, the arrows are flipped. So you just go back and you flip those. So again, you make whatever assumption, you get a negative answer, you basically reverse that assumption. And that's how you deal with 2D particle equilibrium. Free body diagram, and apply your equilibrium equations.